Okay, we'll go ahead and get started. Thank you everybody for coming. Before we start, I'm just going to go through the Zoom etiquette for today. So all audience participants will be muted throughout the presentation. Please do not attempt to turn on your video or share your screen during the talk. There will be an opportunity for the audience to ask questions live at the end of the presentation. Once Amanda has finished her talk, you can use Zoom's raise hand feature to notify me that you'd like to ask a question. And this feature is located under the reactions tab at the bottom of your Zoom window. You're invited to turn on your video and unmute yourself during the questions portion of the talk. So with that, it's my pleasure to introduce Amanda Camarato. I'll be sharing this introduction with Tim Stanton, a researcher at NPS and an MLML affiliate who served as Amanda's research advisor. Amanda came to MLML in fall of 2018. She arrived with a Bachelor of Science in Aerospace Engineering from San Diego State, as well as professional experience in the aerospace industry. But as a San Diego native, she was drawn to the ocean. And in her application to MLML, she described a transformative experience while surfing in Mexico that inspired her to dedicate her skills in physics and engineering to the ocean. And in doing so and coming to MLML, she's been very successful as a student here. She is a recipient of the MLML Student Body Scholar Award, served as a TA for both physical oceanography and data analysis techniques, and has already started on the next phase of her career. Has started a job at Scripps as a data systems analyst. So around the time of Amanda's arrival here at MLML, Tim Stanton had just started up a new observational program in the Arctic, and had an opportunity for a student with physics and engineering skills like Amanda to participate in fieldwork and base a thesis around those observations in a really important part of the ocean and climate system. So I'll let Tim introduce this aspect of Amanda's work here at MLML.
Yeah, thank you, Tom. Yeah, I've really enjoyed working with Amanda on this project. It's actually part of a continuing series of observational programs I've been involved in the Arctic, spanning the last decade and a half, a time in which there's been massive changes in the ice cover, as most of you know, pretty much in response to the ongoing climate change. So the project that Amanda participated in is funded by the Office of Naval Research. I also have National Science Foundation funding that contributed to some aspects of this. And the project name was SODA. And I had the particular joy of being able to include Amanda on a field trip on the Healy that's on the title page that you're looking at now. The big Coast Guard icebreaker. And normally it's very difficult to get slots for students, but we managed to do that. And she contributed significantly in the field program and also in preparation of other components of the instrumentation that we deployed during that project. And with that, I would say again that I've really enjoyed working with Amanda, even through the pandemic. Luckily, we had the benefits of Skypes and those kinds of meetings and managed okay. And I'm particularly pleased that Amanda is continuing her career in oceanography at Scripps. So take it away, Amanda.
Thank you very much, Tim and Tom, for the introduction. I'm going to turn my video off here and then get started. So thank you for being here so I can share my master's thesis at Moss Landing Marine Labs with you. My name is Amanda and my project is satellite remote sensing and model reanalysis estimates of upper ocean heat content in the Canada Basin. Here is a brief overview of the presentation structure. The objective is to introduce you to sea ice in the Arctic Ocean, how it melts in the summer, and offer a thermodynamic analysis of this process for the summer of 2019. And finally, to share some key takeaways learned from this analysis. So first up, I'm going to introduce sea ice and the Arctic Ocean. Sea ice extent has declined significantly since satellites started to monitor it. And these images are from the National Snow and Ice Data Center, and both are regularly updated. But the map on the left shows the area of ice in white for this October, and also the median ice edge, which is drawn in pink. Even though it's hard to see, the point is to see the white area where the current edge is. And then the figure on the right shows the amount of sea ice in square kilometers each month since 1979. And the y-axis represents the extent in millions of square kilometers, and the x-axis is time. So the black line are a data representation of the extent shown on the map in the left. And then the blue line represents a 9.8% per decade decline, which is equivalent to an area twice the size of Alaska. So every 10 years, we're losing 2 Alaskas worth of sea ice. And understanding how sea ice gets to this minimum value each year is important in order to predict the future of the ice cover. So there are many impacts to declining sea ice, and one of them is with a decrease in sea ice, naturally will come an increase to human activity, which includes tourism, commercial shipping, and a military presence, and all of which are difficult to predict the impact that it'll have to the environment. And also with decreased sea ice will be inevitable changes to the ecosystem, which currently relies on the presence of sea ice. And a third impact of less sea ice has to do with a term called Arctic amplification. And it's used to describe how temperatures rise higher in polar regions than they do at lower latitudes, and how the Arctic is warming 2 to 3 times as fast as the rest of the planet due to sea ice loss. And because of these impacts, understanding the thermodynamics of summer ice melt is important for evaluating the key aspects of the climate and its variability. So next, I want to share a sea ice visualization from NASA. And this shows the natural waxing and waning of sea ice cover in the Arctic. And this center gray area, which looks like clouds, is sea ice cover for 2015, starting in February. And before I play this animation, I want to point out, focus, this is an area that we're interested in right here. So this is starting in February when sea ice extent is at a seasonal maximum, and ending in September when the sea ice extent is at a minimum. And this is normal seasonality for ice cover in the Arctic, where little to no sunlight in the winter allows sea ice to grow, and where constant sunlight in the summer melts ice. And then notice at the end of the summer, there's still ice present from the winter. So now that we know about the natural seasonal cycle, I want to share the unique bathymetry and a circulation pattern in the Arctic, because it's linked to the state of sea ice. The Arctic Ocean is surrounded by land and these shallow shelves shown in light blue, and then the middle contains deep basins shown in this darker blue. And in this chart, Canada and Alaska is in the bottom left. And within the Canada Basin is the Beaufort Gyre, which has an anticyclonic circulation pattern. And this pattern recirculates and retains water and ice, which greatly influences the Arctic climate variability. So now I'm jumping into the specifics of what is happening in the summer to sea ice and the upper ocean. So ice can be bare or covered in snow, and then melted snow pools into melt ponds on the surface, and more cracks and open water appear. Also, ice can have various thicknesses, and the upper ocean can be illuminated with sunlight or obstructed from sunlight depending on the surface and ice properties. So in the summer, solar radiation shining on the surface reflects different amounts based on each of them. So open water, or ice reflects about 85% of the incoming solar radiation, and open water only reflects 5%, and then melt ponds can reflect between 30 and 50%. And these proportions are called albedo, or the proportion of incident light backscattered off the surface and back into the atmosphere. And another important term associated with this is solar radiative partitioning. And it's a way to parameterize the total surface albedo in a given area. And it describes how incoming solar radiation is partitioned or divided up into the various pathways where it enters the upper ocean. And it also describes how heat is deposited in the upper ocean, which is important in understanding how sea ice changes each summer. So as that solar radiation enters the upper oceans in those pathways I just described, it can do about two big things. One is heat up the mixed layer, or it can be used to melt ice from the underside called basal melting. And a term associated with the heat is called upper ocean heat content, which is heat contained in the upper layer. And I will get to that, what the upper layer is on the next slide. But studies in various areas in the Canada Basin have found that sunlight that enters through open water alone can account for the observed basal melting. And because of this, it's important to have an accurate understanding of how much open water there is in a given area. So in order to understand the disposition of incoming solar radiation, I want to introduce you now to a thermodynamic framework to evaluate where heat is coming from and where it's going. And this will help us understand processes that set the ocean temperatures and drive heat fluxes. So first, this term labeled QML is the vertical integration of heat in the mixed layer, and it represents heat storage. And then first up on the heat source list is the latent and sensible atmospheric heat exchanges with the ocean. Next is incoming downwelling long and shortwave radiation that's incident on the ice and the ocean. A third is heat source is vertical diffusive heat at the base of the mixed layer. The Arctic is unique in that this surface layer is cooler and it sits on top of a warmer, saltier layer. And diffusive interactions at the base of this mixed layer can slowly mix heat up from below. And then the last heat source is conductive exchanges between the ice and the ocean. And then the heat sinks consist of the latent heat of melting ice, outgoing long wave radiation, and ocean to ice conductive exchanges. So putting these terms all together into a formula, QML here represents heat in the upper ocean. And then these terms in orange represent the heat flux sources, and the terms in blue represent the heat flux sinks. And together, these terms can be expressed by this formula, which is the heat content of the upper layer is the integral of heat flux sources differenced from the heat flux sinks throughout a solar season. And so the integral represents the solar season and dt represents each individual measurement at every half hour. So given the need to better understand the mechanisms of sea ice melt as it relates to incoming sunlight each summer, I set out to construct a 1D heat budget in order to address these three objectives in the Canada Basin for the summer of 2019. The first one is to compare predicted incoming heat with upper ocean heat and basal melt, which means that incoming solar radiation through open water is compared to in situ observations of heat. The second is to compare ice concentration data from a standard source with a more experimental source. And the third objective is to investigate additional heat in the system. So in order to create that 1D heat budget, I need several different types of data from several different sources, and I put them into three main categories. One is atmosphere, sea ice, and ocean. And for atmospheric data, I used incident shortwave down estimates from model reanalysis, which is sunlight in the visible range that's present on the surface. And then for sea ice, I used two different types of data. The first is local concentration in a 15 to 25 kilometer radius in a given area, or how much water or ice there was on the surface. And then the second was in situ measurements of ice thickness. And lastly, for the ocean, I used in situ measurements of temperature, conductivity, and pressure, which also I derived salinity and density from as a function of depth. And so now I'm going to explain the details of each pieces of those data. And for atmospheric data, values for visible sunlight are from model reanalysis. And model reanalysis is a process that uses in situ observations as a baseline to an atmospheric model in order to provide the most complete picture of past climate. So local incident shortwave down data was gathered for a 28 by 28 kilometer grid. So incident shortwave down, as a reminder, is just the visible sunlight shining on the surface. So ice thickness and ocean profile data are from in situ measurements taken from buoys that were suspended in an ice flow. And this image on the left is an installed weather, wave, ice mass balance, and ocean buoy. And it was deployed by the British Antarctic Survey. And this provided ice thickness data. And ice thickness was derived from temperature string measurements at 2 centimeter spacing installed in a narrow hole through the ice. And it kind of looks like this. And then the ocean data were gathered from ice tethered profilers deployed by Woods Hole Oceanographic Institute. And the image in the middle there is the team mid-deployment. And you can see in yellow on the right is the surface buoy. And that rests on top of the ice where the instruments are suspended from. And then this is an ITP schematic, and it shows the surface buoy positioned on top, and then hanging from the ice is a crawling profiler which measures the temperature, pressure, and conductivity. And this profiler takes measurements every 2 decibars as it crawls up and down the wire from about 8 meters deep to 800 meters deep every 6 hours. And sets of these buoys were deployed as part of the stratified ocean dynamics of the Arctic experiment in 2019 in 3 different clusters in the Canada Basin. So as each buoy drifted with the ice flow and collected data, its position was reported. And what you're seeing in these maps are the GPS tracks for the summer of 2019. So starting on May 10th and going through August 28th. And the diamond represents the last reported position. So in panel A, we can see there are 3 different clusters that were deployed. And I want to point out that this cluster 3 here kind of skirted around the shelf, and then it crossed over into a shallow area. But clusters 1 and 2 remained in a deep basin. And this was required in order to actually create a 1D heat budget because it's isolated from advective heat sources, and cluster 3 unfortunately is susceptible to a lot of advective heat from shelf interaction processes. So panel B here is zoomed in on clusters 1 and 2 to show that they remained in a deep area. And the results that I'm going to present here are going to focus on cluster 2, which is in the red. So for ice concentration, I used 2 different types of data, both from satellites. The first type is the most widely used source. It's called satellite radiometer. And it works by measuring the naturally emitted black body radiation from the Earth's surface. And this picture on the left is a depiction of that sensor. And it's showing the satellite here in orbit, and then the path that it takes are these dashed lines. And then the antenna footprint here is the area on the Earth's surface that is being measured by the sensor. And the specific sensor for the data used in this study is called SSMI. So ice concentration data from the SSMI sensor is a data product by the National Snow and Ice Data Center, and users can go download it, and it's what I used for ice concentration. But ice concentration is determined from several of these footprints where multi-channel black body emissions were measured, and then they were averaged into 25 kilometer squares called temperature brightness. And temperature brightness is then converted to ice concentration based on typical emission signatures of ice and water. And the ice edge map that I showed you in the beginning was created with similar data. And passive microwave sensors really excel in the winter, and they also excel at detecting the ice edge, which is why it's the standard used for ice concentration. However, in the summer, there is a larger uncertainty when the surface is dominated by phase changes, or when there's melting snow and ice present on the surface. It struggles to determine the difference between ice and water. So the second type of data from satellite for ice concentration that I used is called SAR, which stands for synthetic aperture radar. And SAR is a sensor that transmits microwave signals and then measures what is reflected off the surface over a very narrow range of band detection. And this sensor depiction seen on the left, the indentation on the Earth's surface is showing where those signals are being transmitted and then received back from. And then the image on the right is what is detected from one swath or one area on the surface of the Earth. And it's different than satellite radiometer data, and it almost looks similar to a black and white photograph. However, the grayscale in this raw SAR image, pointer, this raw SAR image, it's determined by how each transmitted signal is reflected. And so the intensity of each pixel, or how dark or light it is, represents a property on the Earth's surface. So for example, calm ocean would reflect almost nothing, and then it would appear as black in the image, or something like snow would reflect a lot of the transmitted signal and appear as white. But it's not exactly that straightforward. Other things like wind roughened waves can be at the same frequency as the transmitted signal, and therefore it could backscatter brightly and appear as if it's snow or thick ice. So more processing is needed on the raw image in order to determine ice concentration. But a big plus for SAR is that it has a really high resolution, because each one of these pixels covers an area about 20 by 20 meters. And also these transmitted signals can go through clouds. So in order to determine ice concentration from the raw SAR image seen on the left, a binary version was created where each pixel was classified as either being water or ice. And that is what is on the image on the right. And so this image and the matching ice masks that I'm showing you are for cluster 2 on August 25th of 2019. So the raw image in the left, you can see a bunch of gray textures and chunks of ice. And the ice mask on the right shows that binary representation where the grayscale is removed. And these data were targeted SAR captures over the clusters as part of the SOTA Cruise data set. And these matching ice masks were generated by the CSTARS facility at the University of Miami. And CSTARS stands for the Center for Southeastern Tropical Advanced Remote Sensing. So before I get into putting together the heat budget, this is a drone capture picture here, and these little clumps of dots here is the team installing the ITP, and then these little dots here in the middle is the team that's installing the ice mass balance. So the upper ocean heat budget terms are comprised of one source term and 3 sink terms. The source term is shortwave down through open water, or how much solar radiation enters the upper ocean directly through open water, and it's designated as QRAD-OW. And the first sink term is QML, which is ocean heat storage. And it's the heat contained in the upper ocean. And the second sink term is the energy used to melt ice from the underside, called QLH ice. And then the third sink term is conductive heat exchanges with the ice in ocean, labeled as QCOND. And then the residual here is heat that is not represented by the model. So in a perfect model, if I got all the sources and sinks right, the residual would be equal to 0 because the heat sinks would balance the heat source. But this model is only including shortwave down through open water, which means that I'm expecting this to be a lower bound estimate of heat in the system. So this model also shows that all these terms are added together, but I want to point out that the source term is a positive value and the sink terms are negative. And so you'll see these sign conventions later in the figures when I show seasonal values for each of them. So before I get into how much sunlight gets in through open water, I want to briefly share how I got open water fraction from both concentration sources. So first, SSMI data was downloaded as ice concentration for a 25-kilometer area. So to get open water fraction, I simply took 1 minus that concentration. But SAR took a little bit more work. Here are 4 panels that are showing 2 different examples. And the images on the top shown in A and C are 2 different raw SAR images, and their matching ice masks are in B and D, where B matches A and D matches C, so they are vertically paired. And my intent with showing the pairs is to point out that what might look like open water or ice in the original image isn't necessarily what was determined to be water or ice in the classification process. So in each image, the red star represents the ITP location when the image was captured, and the red circle represents a 15-kilometer radius around the ITP. So to get open water fraction, I counted how many pixels within the radius were water or ice in the binary image, and I used that to calculate the percentage of water pixels. And so after getting open water fraction for both sources, this is what I got for the summer of 2019. And I first want to point out the x-axis for pretty much all of the data figures. It's going to be the same, and the x-axis represents time, but it's a range of day of year. So it starts on day of year 130, which is May 10th, and it goes to day of year 240, which is August 28th. And for this figure, the y-axis is open water fraction, so how much open water there is. And the blue data represents SSMI-derived open water fraction, and the orange data represents the SAR-derived open water fraction. So taking the solar radiation data from model reanalysis and scaling it to how much can enter the open water, it's represented as FRAD of OW, or the flux, and that's seen here in figure B, where the y-axis is in watts per square meter. And again, SSMI is in blue and SAR is in orange. And you can see that they definitely don't agree from how much open water there is and then how much flux there is. There's definitely a large difference. So for the seasonal totals, this flux is integrated through time using this formula. And the y-axis shows the seasonal totals in megajoules per square meter. And you can really tell here the difference in open water fraction that was in A results in a large seasonal difference between SSMI in blue and SAR in orange, where SSMI estimated almost 140 megajoules per square meter entering through open water, but SAR estimated just over 40 megajoules per square meter. So before I talk about how I determined QML, I want to describe the structure of the upper ocean with these temperature profiles in panel A. So in the top panel, the y-axis represents depth in meters, where the top is 0, or the surface right under the ice. And the most notable part about this figure is the zoomed in temperature scale. It's represented by the colors, and the color bar is in Celsius. And what it shows is that these cool waters on top in the blues and greens, and then the warmer water trapped below the picnic line in this yellow. So in this upper layer in the beginning of the season, the temperatures are cooler and evenly mixed. And then as the season evolves, the upper layer starts to warm up from the surface, but this heat from below stays trapped in the picnic line. And then all of these black dots here represent the interface, and it's the location that I determined to be the integration depth, which I'm going to call Z2. And it's the depth that I use to determine the heat trap or the heat content in the upper layer. And we can see that that hovers around 55 meters for the season. And so I used heat is vertically integrated for each profile with this formula, where QML is determined by the specific heat capacity of seawater, CP, and the reference density of seawater, rho naught. And then the vertical summation of temperature from the depth at Z2 all the way to Z1. And the temperature in the integral accounts for the varying freezing points of seawater. And then DZ represents each depth where these measurements were taken. And the result of this formula is shown in panel B as the summer evolves. So the x-axis is time, and then the y-axis is the magnitude of heat that's getting stored in the upper layer in megajoules per square meter. And I want to note that this y-axis starts at 0 and then it becomes more negative because this is a sink term in the heat budget. So basal melting was determined by using changes in ice depth, and the ice mass balance measured temperature, and this temperature string went through the ice and into the ocean, which is warmer than ice. So the depth where this temperature change was detected is subsequently like how deep the ice was. And in panel A is a time series of this depth. So the y-axis is in meters where the surface is at the top. And then the bottom is the overall depth of the ice. And you can see in the beginning of this series, the depth is relatively flat. So there's no ice growth or melt. And then as the summer progresses, it becomes more shallow. So to convert this to the latent heat to melt ice and determine the energy associated with this, I used this formula where little QLH is the latent heat of fusion for sea ice, rho ice is the density of sea ice, and delta Z ice is the change in thickness. And this formula, the result of this formula is in panel B. And so because this formula uses constants, the shape is the same as above, but it's flipped because this is a sink term. So by the end of the season, about 60 megajoules per square meter went to melting ice from the underside. So before I get into the formulas that I determined the seasonal conductive contributions, I want to show you what the ice temperature profile data looks like. So in panel A on the left are the ice temperature profiles. So the x-axis here represents temperature in degrees Celsius, and the y-axis is depth, where the surface is 0 at the top. And these lines are weekly averages of temperature measured from the surface through the ice and into the ocean. And each color represents a different weekly average, and it matches the dates in the color bar on the right. And I want to point out at 2.8 meters right around here, This line, it shows where the temperature streams, we're all measuring ocean temperatures, which is why there's this straight vertical profile here. So to determine the conductive flux, I use Fourier's law of thermal conduction, where dt dz is a thermal gradient and K ice is a constant. So to determine the thermal gradient at the bottom of the ice for each measurement, I needed to locate the bottom of the ice and then identify successive measurements above it. And panel B is an example of how I determined this gradient. It has the same axes as panel A, but this green star right here represents the location at the bottom. And then these blue stars here represent the data used to calculate the gradient, which is simply the slope. So the units are degrees Celsius per meter. So now that I have the gradient for each profile, I have the conductive flux. And similarly to the accumulated solar radiation, I used this formula to determine the seasonal contributions of heat. So it's also a cumulative time integral. So now I'm going to combine all of those sources and sink terms together. But before I get to that, I want to revisit this theoretical budget from the introduction and remind you that in a perfect model, the residual would be 0 because the sources would equal the sinks. And on the left here is the budget that I used in the methods. And on the right are the source and sink terms from the introduction. And so studies have found, it turns out that diffusive contributions at the base of the mixed layer are small. And so I didn't need to include it. And then because open water fraction was small for this area, so is the latent and sensible heat exchanges. So those are not included. And then it also turns out studies have shown that the net incoming and outgoing long wave radiation are around 0. So that term wasn't included. And what is left was included in this 1D heat budget, with the exception of some shortwave downward is only taken into consideration for open water, which is how this budget is intended to represent a lower bound of heat in the system. So first I'm going to show you all these terms for SSMI together. So this is time is on the x-axis again, and then the magnitude of each term is shown on the y-axis with units of megajoules per square meter. And in blue is QRAD OW. Up here, purple is the conductive heat. Orange is QML, which is heat in the mixed layer. And then at the bottom here is the QLH ice in yellow, which is how much basal melting there was. And then the seasonal budget, or the end of season values, are in this black line here, which is the sum of all those terms. And I want to point out, this is the line we're focusing on now, and that by the end of the season, it shows a positive residual. And a positive residual means that more heat was predicted to enter the system through open water than the sinks accounted for. And this positive residual would therefore indicate that SSMI overestimated ice concentration in this region. So now here is the SAR budget. All these sink terms are the exact same. They're the same for both budgets, but what's different is this is QRAD OW with SAR derived open water fraction. And then this black line here, which is what we're focusing on, the sum of all those terms is also different. And the biggest difference here is that there is a negative residual. And a negative residual means that more heat was measured in the system than was predicted to enter through open water. So SAR derived open water fraction, if you calculate how many heat sinks there was, the open water fraction only estimated 42% of that. So 58% is remaining to an additional source. So here are both budgets side by side. These are the same figures that we just saw, but the y-axis is adjusted to be the same, so that you can really see these differences. And the main takeaway from comparing both is that SAR is a more reasonable estimate for open water fraction than SSMI. And because this is intended to represent the lower bound of heat into the system, since it only accounts for the contributions through open water, SAR is more of an expected result here. And so this leads to the result that estimated incoming heat when using SSMI derived ice concentration is an over prediction, and it's not plausible. So with the determination that SAR is more likely to represent actual ice concentration, but it also indicates that there's the presence of an additional heat source term, and that's represented now as this budget residual, this black line. So to investigate the source term of solar radiation that's transmitted through ice and melt ponds, something that wasn't considered before, the residual was converted to a seasonal flux. So what I did to convert it from a seasonal total to a seasonal flux, instead of taking the integral, I take the derivative of that signal, and panel A is showing this. So it was converted back to a flux, and it's shown in these green dots here with the units of watts per square meter on the y-axis. And all of the variability or noisiness seen in that raw residual flux is due to the combined noise of all the data sources and all the instruments limitations. So to investigate seasonal values in the residual, I averaged it over 15 days, and that's shown by those black dots. And seasonally, the flux ranges from a couple watts per square meter to about 10 watts per square meter. So from this mean, the through ice and melt pond combined transmission was calculated with this formula. And this formula is the ratio of the solar flux at the surface over the residual flux, the 15-day mean residual flux. And then the seasonal transmission is now, what I got from that is in panel B, with the percent solar radiation transmitted is shown on the y-axis. So for this time series, the inferred transmittance ranges from about 0.015 to 0.045. But when comparing to in situ transmittance, a study from Light et al. Observed values between 0.04 and 0.25 for bare ice measured in 2010 and 2011 in the Beaufort Sea. And so what that means is that the ice had was comparable conditions, and it was kind of in the same area. It's still in the Beaufort Sea, but it's in a slightly more southern area. So the inferred transmittance here that I calculated are on the low end of the in situ, the Light et al.'s observations. But keep in mind, this is in a 15-kilometer area, and it's more of a spatial measurement than a point measurement. And these differences could be, they might be attributed to cluster 2 being higher in latitude, where the angle of solar radiation is lower, and shortwave down is spread over a larger area, or the ice could have different optical properties, which affects the scattering and transmittance. But I believe that the transmittance calculated here is a realistic and plausible value, and the residual represents how much sunlight was transmitted to the upper ocean as the additional heat source. So there are two main takeaways from this work. As although many studies have demonstrated that SSMI struggles in the summer away from the ice edge, this study shows SAR-derived open water fraction better represents sea ice concentration in the summer. And also SSMI-derived open water fraction is insufficient to estimate the sinks determined in the mixed layer. And what this suggests is that previous budgets that used satellite radiometer open water fraction estimates in order to directly consider the plausibility of basal melting via direct absorption of solar radiation through open water may have been missing other important processes or contributions like through ice transmission. The final takeaways are that the residual of this 1D budget supports reasonable estimates of local through ice transmittance. And because this is plausible, it reinforces the SAR-derived open water fraction. And when comparing to previous studies in other areas of the Canada Basin, the SAR-based budget indicates that there are regional differences between local radiative partitioning and solar season melt processes. So by understanding the challenges that satellite radiometer faces to detect ice cover in the summer, it can help improve Arctic coupled atmospheric ice ocean models, and it can increase the predicting capacity for the current and future state of sea ice. So knowing how SARs can support these challenges that satellite radiometer faces, it's impossible to increase the predicting capacity for sea ice in the future. And it's also a pretty big advocate for trying to use SAR more. And the study also brings new understanding to radiative partitioning in a region where there's near permanent pack ice. And it also highlights the importance of these in situ and remote observations across the Arctic. If I were continuing this research, I think it would be interesting to combine this method with local ice transmittance in situ data to investigate the applicability to infer ice transmittance on a larger spatial scale in the summer. And one more next step would be to start integrating SAR-derived open water fraction into the coupled Arctic models. And finally, I'd like to thank my committee members, Tom Connolly, Tim Stanton, and Ivano Aiello for supporting and guiding me as I learned how to conduct research, and also in learning that I can never be done. And I also would like to specifically thank Tim for the golden opportunity to see this part of the world. It made all the difference in doing this research. And I'd also like to thank the Moss Landing Marine Lab community for creating an inviting and supportive place to accomplish this research. And I want to acknowledge the funding and technical support required to have this data. And it includes ONR for funding the SODA program, the Sea Stars facility, and John Hargrove for capturing and processing the SAR data. Jeremy Wilkinson from the British Antarctic Survey for the ice mass balance data, and Bill Shaw from NPS for all of his technical support and review. And lastly, I'd like to thank my family for their tireless behind the scenes support and encouragement. And now I would like to open it up for questions.
Okay, thank you very much, Amanda. We'll open it up for questions now. And as a reminder, you can raise your hand under the reactions tab on the on your Zoom window. While we're waiting for, I see John Hargrove. Do you have a question?
I do. Yeah. That way I don't have to raise my hand.
That's fine. Yeah.
Yeah. Appreciate it. Amanda, wonderful presentation. You did a great job, and it was really just nice to see the imagery at work. And of course, we at C-STARS are very happy with your conclusion. I was wondering, do you think, is there a strong difference, or what would you say about the difference between the SSMI and the SAR in winter? Or is that something that you didn't really look at much?
I did not really look at that, but I can show you some beginning of the season values.
Mm-hmm.
I'm gonna try to go back. There we go. So at the beginning of the season here, they both really predict 0, and that's the only time that I saw them really agree.
Right, right.
Look into any sooner than May 10th.
Right, right. So day 140 there, that's like kind of first breakup or first appearances of open water, right?
I think so. If you look real closely at this figure, I had the bigger circles are my actual data, and then the thicker lines are the interpolation between those. And so I don't see a SAR image until like day of year 165, but SSMI is starting to show that.
Yeah. Well, I was wondering, did you have a look at different radius or radii around the Limbo or ITP cluster? Because I think you used, what was it, 15 to 20 kilometers?
So I used, yes, I'm sorry.
To kind of match the SSMI resolution, but whether you could see any effects, because the changes are kind of subtle, I think, but whether that could be, correlated with some of the residual zigzagging you saw, whether that, could be actual real variability where ice was maybe kind of opening up a little bit and packing in again as it changed. What are your thoughts on that?
So I pulled this slide up to kind of talk about that. And I spent about 2 months agonizing over that exactly. And so first off, these images are about 45 by 45 kilometers in area. So if the ITP wasn't exactly centered, then it was a little bit harder to get a larger radius than 15 kilometers. And I analyzed 15 kilometers, and then I halved that all the way down to 2 kilometers, and I compared those values. And then I even took it a step further, and I just used the entire image that I had, without taking into account a radius. And what I found was that I ran it through my whole budget. And what I found was that when including either the entire image all the way down to about 4 kilometers, didn't change the overall budget. It's really started to see that variability in local area when it was about below 4 kilometers.
Okay. Between 4 and 15. Yeah. Another thing that I was interested in for this is, do you recall for cluster 1 and 2, how big is the actual ice flow that the WIMBO is on, and how far are there sensors from the edge? Because if you're looking at, kind of in your intro slides, you were talking about basal melts and, getting solar radiation from the cracks. And so I wonder if there's some effect where the sensor itself, as it goes on in the season and the ice flow gets smaller, than the component of kind of how near you are to a crack, is that getting less? And I'm just wondering if there's some way you could get at that with the combination of being able to see it in the SAR, the detail of the ice with the instruments. What do you think about that?
I think that, well, first of all, the ITP and the WIMBO were installed on the same ice flow, about 100 meters apart, and they were about 1 to 2 kilometers in width, these ice flows. But that was when we installed them in October of 2019. And so there's not, unless you have really high resolution images, there's no real way to know like if or how the ice flow broke up during the summer.
I think we can. I think that the location is enough where, we could zoom in and try to, identify the flow that it saw. I mean, some of them, I get all of them that there were 5 or 6 WIMBOs. I get them kind of confused, and the ones that were in the south behaved a lot differently, than the northward, on very, very large ice flows that eventually just completely dissolved and became nothing. I know there was kind of clusters 1 and 2, the ones further up were kind of less, but like that, but still some of that kind of micro level, looking at the shape of the flow and trying to relate it to the rest of the instruments would be something I would be very interested to work on and look at with you if you are continuing on this project. But anyway, it's a beautiful, great results. I'm very excited to see it, and thanks for using our imagery and products there.
Thanks, John.
Amanda, I have just to follow on to John's question. It turns out that the response of the ice for basal melting, it's a turbulent transfer that is really integrated over, hundreds of meters upstream, kilometers, in fact, that the ocean actually acts as a real integrator, that you're very unlikely to see edge effects unless you're very extremely near an edge. And there's a lot of physical arguments that support what I say there. So I think actually the basal melts, even though they're just single points in each ice flow, are really very likely to be very representative of aerial averages because of the way the turbulent mixing happens in the ocean. You do, however, in late summer, when you get big leads, you can certainly see when the ice gets shoved over a warmed area, like a lake, as it were, that's been warmed by the ocean. You really see that, and that, for example, is in Gallagher's PhD thesis from the MISE experiment. He explicitly looked at that. But in general, the ocean is a really good spatial integrator. So I wouldn't expect strong edge effects as the flow.
Well, do you think that maybe that's related to the 4 kilometer number that Amanda was talking about? That, I mean, that's kind of what I recall when I looked at this long ago, or a while back too, is that, yeah, there is kind of, you can see some differences from when you go from 20 to the whole image down to 15, 10, below 2 to 4. Yeah, not really any different, but that could be related to the size of the flow. But I guess also, for sure what you're saying, this integrated effect where, right. But that's good. That's good for.
Yeah, no, it's good also for the flux measurements that I make with the AOFB, of course. And the other point that Amanda was making, I just want to emphasize, is that this 15-kilometer radius was deliberately chosen to be close to an SSMI 25-kilometer square grid.
Right.
Because we were trying to do apples to apples as to the extent that we could in these quantitative comparisons.
Well, that reminded me of one thing. it's the SSMI and the AMSR. I think I was talking to the group at Bremen about these kind of comparisons and time of year, and he said, you know, if you really want to do that, I mean, there's definitely value in just to download the standard product, right? Which other SSMI people or other scientists around the world are using, but they can create like from radiometer images and apply the SSMI algorithm. So you don't have the gridding, and they can make a much higher resolution product custom, you know, for if you want to work, you know, work with them, which is kind of like the way the SAR is. It's kind of an unfair comparison. Well, we order these images and work with each one, you know, an hour or two. SSMI, it's just always running, producing massive amounts of data. But, you know, it would be, that's another interesting thing to look at where this research could go if you were, you know, kind of wanted to understand in more detail what's the strengths of the two methods is to look at the SSMI and a kind of higher temporal and spatial resolution. It is possible.
Yeah, it's a good point. Amanda can do that this weekend.
All right. What are your plans, Amanda?
I was going to start with.
I'm sorry, I missed the introduction. I'm sorry, the introduction.
Oh, you mean this? I'm working at Scripps as a data analyst in San Diego.
Okay, what kind of data? What kind of group? What's the group?
It's atmospheric data. It's the Chord C group.
Okay, great. Well, hopefully I'll be seeing this in a publication at some point, I hope. Excellent.
Well, thank you, John, for your questions. I don't see any other questions from the audience, but I have a question of my own. The transmission estimates, previous observations that you cited, they don't account for melt ponds. I think just transmission through the ice. How does that affect your interpretation? What's happening?
So it's a scene. Let me go to the slide real quick, Tom. So I think that this like seasonal variation in transmittance in panel B can kind of reflect that, where we see the values go up and down a little bit. So I think that transmittance will be a lot higher when there's melt ponds, but there's also these ephemeral processes where melt ponds will, once they fill up, they'll actually drain, and so there'll be bare ice again. So it's difficult to say, but I think that this range throughout the season represents mostly ice.
And in fairness, it's a very good point, Tom. It's a composite ice and melt pond transmittance, and there's certainly no way that we can distinguish without in situ measurements, which we oddly enough we did have in MISE. We had video cameras on some of the buoys that in Sean's one of Sean's papers he reports, and was able to actually see the melt ponds draining and the effect on the ocean. But in this case, we didn't have that resource.
Okay, thank you. Well, I don't see any other questions. So before we meet with just Amanda's committee, I'd like to invite people to turn on their cameras and congratulate Amanda over video.
Congratulations, Amanda.
Thank you.
Well done.
Congrats,
Nice,
Amanda.
nice job, Amanda.
Thank
Nice
you.
job, Amanda. Congratulations.
Thank you.
Congrats.
Such an awesome presentation.
Okay, well, thank you everybody for joining us. And thank you again, Amanda.
Thank you.
Congrats.
Yay.